Hello YouTube, this is part 4, how to build a Raytracer from scratch in C++. Last time we created a function that we could pass a data type to with red, green, and blue values that created an image on the hard drive. And then we assigned a color to our red, green, and blue values and restricted that color to only a center portion of the image, and then sent our color to our function, and that's what we got. So now we're ready to start extending our Raytracer to thinking about how we're going to model things like the camera, the sphere, planes, the light. And in order to do those things, we have to do a little bit of linear algebra. Now, linear algebra is a subject that involves vectors, the dot products of vectors, the cross products of vectors, normalizing vectors, finding the magnitude of vectors. So it's helpful if you don't know those things already to brush up on those things, but I'm going to show you a few of them and kind of show just enough of the details to help keep you interested and keep you going, because it can be overwhelming at times. But how a Raytracer works is you use object-oriented programming to model objects like cameras and spheres using vectors and coordinates in 3D space. And that's how we model 3D spaces, with vectors and coordinates. So for our camera, we have a location and we have a direction that it's pointing, and that's going to be our two vectors that we need to supply to our class declarations in order to model a camera in C++. So we're going to start by declaring a class of vectors. We're going to shorten it to vect. Create a new file. Save as vect.h. And this is where we're going to define our class. Going to be a public class. That's how the class is declared, with no parameters. This is the general constructor function. We're going to give it some method functions. And we'll use these method functions from within our main program to return the individual x, y, and z coordinates as we need them. We're going to add some more of these as we go. So this file isn't finished yet. But we can go ahead and move down here and set up the parameters that the vectors should have if you don't supply any arguments. And this is how the parameters that we do pass to the vector actually get assigned to the x, y, and z coordinates. So we can call instances of vector. We can give them x, y, and z coordinates, locations within our scene. And then we can return those x, y, and z coordinates from within functions by calling the name of our vector .getVect x, y, or z. Let's compile and make sure we don't have any errors. There. Now we're going to create a new class that's almost the same as vector, called Ray. And since it's so similar, we're going to go ahead and copy everything here, create a new file called ray.h, and then because we're using Crimson Editor, we have a nice little way of highlight the word we want to replace. Press Ctrl R, and then we're going to replace it as Ray. Replace all. Capitalize these. But rays are different from vectors because they're made of vectors, and they have two vectors associated with them, an origin and a direction. So these are two vectors that each ray needs to have. And the method functions of our ray class, like this. Default parameters. So this says if we create a new ray within our scene, a new light ray, for instance, and we don't tell it what its origin is or its direction is, then we want our class to specify that the default origin of a vector is the origin of a 3D scene, and that the direction is in the x direction. We're allowed to supply our own origin and direction if we want to. sure we don't have any errors. We can use the vector class within our main function by creating a new instance of the vector class. And we'll go ahead and create 3 vectors which correspond to the directions x, y, and z. And now we're ready to model a camera. So we're going to define a new class called the camera class. Create a new file, save it as camera.h, copy one of our other class declarations, and then we're going to be replacing Ray with camera. Cameras have parameters that are vectors, like the Ray does, except now we have 4 of them, where they are the cam position, the cam direction, cam right, and cam down. And these parameters are used to define general coordinate system for our scene, and they're used within our method functions that we're going to be adding to vector in order to compute our perspectives. Now that we're supplying 4 vectors to camera, we can tell it to expect those. Where our method functions change to position, direction, right, and down. We'll let the camera default camera direction be up, which is the Y direction. No, the Z direction. We want our default camera to be in the Z direction. We're going to let right and down both be the origin, because we're going to specify the right direction and the down direction from other variables later on. And the way that we supply these new parameters are telling our camera class to expect those new parameters. Compile, make sure we don't have any errors. We're good. And now we're ready to create an instance of the camera in our main function. But before we can do that, we need to define some method functions for our vector class that perform some custom linear algebra. One of the linear algebra operations we can perform on a vector is to normalize it. And the result from normalizing a vector is still a vector. We need to define the magnitude of the vector, which is a scalar. Where the magnitude of a vector is the square root the x-coordinate squared plus the y-coordinate squared plus the z-coordinate squared. And to normalize a vector, we return a vector that has 3 coordinates which are normalized. Just checking my spelling. So we can normalize a vector from within our program by typing the name of the vector or the instance name dot normalize parentheses. Another method function we want to add is negative. We want to be able to invert a vector in the opposite direction. And we do that by returning a vector that has the negative of the x, y, and z values. Let's compile. compile, make sure we don't have any errors. Another thing we can perform with vectors is a dot product. The dot product has a value of a scalar. With the dot product of the vector is a scalar, and it's the x-coordinate multiplied by the vector that we're dot product it with, x-coordinate, plus the y-coordinate of the vector that we're dot plotting. Times the y-coordinate of the vector that's being dot product with it, and the z-coordinate follows. The other operation that often gets confusing is the cross product, which is a vector. Where the cross product is a vector with the coordinates This says that the cross product of two vectors is the y-coordinate of the first vector times the z-coordinate of the second vector minus the z-coordinate of the first vector times the y-coordinate of the second vector, and that's the x-coordinate of the cross product. And then you do the same thing with the y-coordinate and the z-coordinate. Let's compile. You need to be able to add vectors. Lastly, we need to be able to multiply vectors. Scalar multiplication, that is. And now we can do anything that we need to with the vectors that we declare. And for our camera, to define the position, direction, the right and down coordinates, we're going to be using some vector operations. We're going to be defining the direction of the camera by creating a vector called look at. And for now we'll let that be the origin. And I'm going to go ahead and write this line down and then describe what it does. The vector diff between has 3 coordinates, and those coordinates are the difference between the x coordinate that we give our cam position minus the x coordinate that we gave look at vector. And the y coordinate is the difference between the y coordinates, and the z component is the difference between the z components of those other vectors. We can define the camera direction as the difference in the opposite direction normalized. So what this says is that we're defining a point that we want our camera to look at. We get the difference between our camera position and the point that we want to look at, and then our camera direction is going to be a normalized vector that is in the opposite direction of the difference between the vector between the camera and, in this case, the origin. We're going to find cam right as the y vector, where y is this vector up here. cross product, our cam deer. So this is saying cam direction and y, and you can think of this as a cross product between those two. So this is y cross cam deer, and we normalize that as well. Cam down is going to be cam right dot so cam down is cam right crossed with cam deer. Finally, we can declare an instance of camera. Where the only thing we're missing is our definition for cam deer, or cam position, sorry. We're going to arbitrarily set the cam position just so long as it's above the y plane. Let's compile. Great. So what we have now is a Raytracer that models a camera with object-oriented programming. The last thing we're going to define for today is a class called color. Let's get a new file, save it as color.h, which is very similar to vector, so we're going to copy it and replace vect with color. Where in our case, we're going to use object-oriented scalability to supply another argument called special. The method functions are get color red, green, blue, and special. Where instead of having extra method functions this time, we're going to have some setter functions. where we supply our own values for these colors. Where we're going to have a default color of, let's let the default color be gray. Let's compile. Very good. And we'll need to add some more method functions to this in a little while. But for now, we're far enough along to go ahead and model light too. So we're going to create a new class for light. For light, we're going to use our ray function as our template, replacing ray with light. Where light includes both our vector class and our color class. The two arguments that it expects are a vector and a color. Our get functions now return those values but these are virtual values. We'll let the default position be the origin. And the default color be white. Where our color class expected red, green, and blue values, and then a special value, which we'll let be 0 for now. Let's compile. Uh-oh. Okay, it didn't like these virtual declarations. We'll remove them for now. Oh. Typo. Okay, that cleaned it up. So wait until later until I describe why these have to be virtual functions. Or virtual values, in other words. But now that we have a light class, we can create a light in our scene. We also have a color class, so let's create some colors too. Where we're going to use our special value to add reflectivity and shininess to our surface and our colors. And of course black is all zeros. And now we can create a light or a light source. Which has a position. We're just going to put off to the side. So these are three-dimensional coordinates, and that's where we're placing our light. Let's compile. Awesome. So we're well on our way to creating a ray tracer, one that has camera, colors, and lights. And we're going to use these elements in the next tutorial to start thinking about how we create shadows and perspective and reflections. So I hope you stay tuned. Thanks.